All right. Uh, Jeremy, ready? We'll get you going here. So thanks everybody for coming on today. Today's webinar, USPTA Eastern webinar series. Today we're lucky enough to have Jeremy Rosen. Jeremy is a USPTA professional, former college tennis player, and he's currently pursuing a PhD in economics. He runs a tennis analytic website, Topspin Shot Research, where his goal is to employ advanced statistical techniques to help players and coaches better contextualize traditional tennis statistics. He also conducts sports economics research for tennis, football, and baseball. His research has been featured in Tennis Player Magazine, Football Outsiders, Baseball Prospectus, Contemporary Economic Policy, and Georgetown Center for Economic Research working papers. He's currently co-authoring a paper with Georgetown University economics professors that uses dynamic game theory to uncover suboptimal serving strategies in the ATP and WTA Tour. Today's webinar, Interpreting Tennis Statistics. And Jeremy, I'm going to toss it right over to you now, and you can start it up. Oh, and everybody, today's webinar is being recorded.
All right, thank you, Jason. So I'm just going to share my screen now. PowerPoint presentation. Here we go. So, before I get into anything that is specific to tennis, I'm going to start with a non-tennis story about the theme of today's webinar, which is the importance of correctly interpreting statistics. So this is the story of Dr. Abraham Wald. Dr. Wald was a statistician who worked for the Allies in World War II. And he was given a very specific task by the military officers. So what he was shown were a bunch of planes that had come back from combat. And these planes had bullet holes in them because they had been fired upon by the Axis powers. And military officers told Dr. Wald that they wanted to increase the amount of armor to protect the planes from bullets. The issue, though, is that too much armor and the planes will be too heavy to fly. So Dr. Wald is being tasked with looking at the patterns of the bullets, which are essentially statistics, to determine what's the best place for the armor to go. And if you look here at the plane, it's pictured on this slide, you look at all the bullet holes, you'll notice that there's a lot of bullet holes in the body of the plane. And there's a lot of bullet holes in the wingtips. But what you don't see are any bullet holes on the engines, because that's exactly what Dr. Wald saw. There were virtually no bullet holes on the engines. So kind of the most intuitive thing, right, what you'd first think is that you would want to put the armor where the bullet holes are. That way you'll best protect the plane. But Dr. Wald didn't just stop there. He thought for a second, essentially asking himself, why is it that the patterns of bullet holes are the way they are? And he realized something, which is that the planes that he got to see were not all the planes that had come back from combat. And if you think about it, I mean, the Axis powers are firing bullets up into the sky. I mean, they're not snipers. They're not specifically targeting parts of the plane. They're just firing bullets up there, and whatever they hit, they hit. So why is it the engines are seemingly not getting hit? Well, what if they actually are getting hit? And what's happening is that the planes that get hit in the engines are just crashing, so they don't come back from combat, and Dr. Wald never gets to see them. So what Dr. Wald realized is that the initial intuitive hypothesis that the armor should go where the bullet holes are is actually not correct, and in fact, the armor should go where the bullet holes aren't on the engines. And the military officers thankfully listened to Dr. Wald, and then that ended up saving a lot of lives. So, with that in mind, what can we take away from this story? Well, first of all, while statistics are important, I mean, statistics are definitely important without being able to look at the patterns of bullet holes on that plane. I mean, Dr. Wald wouldn't have been able to come to any conclusions, but what's even more important than the statistics themselves is the act of correctly interpreting them, and the reason for that is one small oversight, right? You can understand 90% of the problem perfectly correctly, But one little oversight, like in this case, the fact that the planes that Dr. Wold got to see were not the entire sample of planes that had gone into combat, one little oversight can lead to a giant mistake. Not only, understanding 90% of the problem makes your answer 90% correct. In fact, you could get the complete wrong answer where you would have actually been better off if you never saw any data in the first place. Because that one oversight would have led to Dr. Wald telling the officers to put the body armor in exactly the wrong place. So that brings me to the framework that we're going to use for interpreting statistics. This is kind of a general framework that's going to be mentioned throughout this webinar. It's called causal inference. Causal just means cause and effect. That's all it means. Inference is the act of figuring something out. So if you put it together, causal inference is the act of figuring out why statistics are the way they are. That's exactly what Dr. Wald did. That's exactly what we're going to do going forward. Now, at the beginning of every talk that I give, I like to start with a promise. Not necessarily a big promise, even just a little promise, but something that I say in this talk you're going to be able to take away from it. Something that's going to change the way you look at something going forward. And because this is kind of a special talk, I'm actually going to make two promises. The first promise is that something I say at some point in this talk is going to ensure that coming out of this, whether it's in tennis as coaches or whether it's even in the world outside of tennis, you will never quite look at statistics the same way again. As for the second promise, I'm going to save that one for the end of the webinar. So I'll keep you in suspense. And without further ado, let's get into the tennis. So, how effective is playing the net really? Whenever I learn something, I always find that it's easier to learn by an example rather than just throw a bunch of terms and definitions at you without context. Oftentimes, it's just easier to convey it through an example, so that's exactly what I'm going to do here. I'm going to convey how to use causal inference through an example. This example is how effective is playing the net as opposed to staying back at the baseline. As far as what I mean by effective, well, in the words of the former New York Jets head coach, Herm Edwards, you play to win the game. And as a result, what I'm going to be looking at is first thing I'm going to look at anyway is win probabilities. Playing the net, staying back at the baseline, got some win probabilities here. These are from a publicly available online article by Craig O'Shaughnessy, the strategy coach. He got data from the ATP on the left side and the WTA tours on the right side. This is from 2002 to 2015. And if you notice, it's very consistent across both tours and years. Players tend to win 65, 66% of the time when they approach the net. They tend to win only 45, 46% of the time when they stay back at the baseline. So this is something that is extremely consistent. And the way that Craig O'Shaughnessy interprets it, this is a quote that's taken from his article. He says it's a really easy, straightforward question. Do you want to play more points back at the baseline where your win probability is 46% or less than that? Or do you want to develop your net game to create a larger group of points for yourself where you can win 65, 66% of the time? And he concludes by saying it's a no-brainer. Or is it? I mean, it seemed like a no-brainer that, with Dr. Wald, that the armor goes where the bullet holes are, and yet it's simple. Either. Let's start with kind of a hypothetical scenario. Before I get into a formal match analysis, this is just a hypothetical scenario. Imagine that somehow I've been morphed into this world-class tennis player, and I am playing Novak Djokovic. I serve 4 points to him. The first 2 points are like the one on the left here, where I have some great serves. Djokovic floats to returns, barely gets those things back. I approach the net. So, I got this nice floated return. I approach the net, put away a couple volleys. I win both points. My win probability is 100%. The other two, Djokovic, as you can see on the right, hits much stronger returns. He blasts them at me. I'm not approaching the net on these. I'm staying back, playing some defense. And since I'm a good grinder, I managed to grind out one of the 2 points. and I end up with a 50% win probability. So with that in mind, I mean, I do have a 100% win probability at the net and a 50% win probability when staying back. Should I have approached more often, right? Was coming to net actually a more effective tactic than staying back? Well, causal inference. Let me ask myself, why are the statistics, in this case, the WPs or win probabilities, and throughout this presentation, I'm going to abbreviate win probabilities as WPs. Why are the win probabilities the way they are? Well, it really comes down to the quality of the incoming ball, even more so, right, than the fact that I happened to approach the net on the 2 points that I won. What really mattered here was not so much the act of approaching the net. What really mattered was the quality of the incoming ball. And therefore, I really shouldn't have approached more often, because if you think about it, if I did approach more often, I would have had to try to approach the net on a return that was blasted at me. I probably would have lost both those points trying to come in on blasted returns. So in fact, if I just compared the win probabilities and decided that I should approach more often, I probably would have won fewer points, which means that in general, having a higher win probability at net does not necessarily mean that you should approach the net more often. Again, I'll repeat that. A higher win probability at net doesn't necessarily mean that you should approach the net more often. So now, I'm going to do a formal match analysis. So that was just a hypothetical scenario, no real data or numbers. I'm going to start giving some numbers here. This is a match that I analyzed. I charted it by hand. I bought a DVD of the match. You can kind of see it here. This is the 2016 Wimbledon final. Andy Murray versus Milos Raonic. Murray won this match 6-4, 7-6, 7-6 to win a second Wimbledon title. And what's great about this match, the reason why I chose it, is because of the great contrast in styles. Right? Murray is this steady counterpuncher, whereas Raonic is the attacking player with the big serve and the big forehand. So it was just nice to get a contrast to styles. But what I'm going to do is I'm going to formally analyze this match in terms of how effective is playing the net really. Before I do that, though, confounders. Confounders are a statistical term, all right, that I'm gonna introduce here. This is not a tennis term. This is a statistical term. And what are confounders? So confounders, first of all, are variables other than approaching the net. So confounders, approaching that is its own variable. Confounders are something else that has two key properties. The first property is that confounders affect your odds of winning the point. So it's something that happens, some variable over the course of the point that does in fact, just like approaching the net can affect your odds of winning the point, a confounder can affect your odds of winning the point. It also affects your odds of approaching the net, right? Just like the quality of those returns in the Djokovic scenario, right? Having a floated return definitely impacts your odds of winning the point. It also impacts your odds of approaching the net because you're more likely to come in on a floated ball. Examples of confounders, these are kind of the three basic confounders I'm going to use when I really get into the Murray-Raonic match. The depth, direction, and speed of the incoming ball. So the depth is just, did it land short or deep? Right? Did it land inside the service line or past it? The direction, as in was it in the center of the court? Was it centered or was it hitting the corners? And lastly, the speed. Essentially, was it hit hard or was it floated? And the thing with confounders is, they're called confounders because to confound is to confuse, and they can confuse you. Like with Dr. Wall, right? The confounder there was that you have a situation where not all the planes that Dr. Wall, that Dr. Wall did not get to see all the planes that went into combat. So in this case, the point is that when you have confounders that affect both your odds of winning the point and your odds of approaching the net, they can confuse you and cause you to draw the wrong conclusions. So when I set up this analysis, first thing I always do, right, whenever I'm setting up any sort of statistical analysis, which is exactly what I'm about to do here for the Murray-Raonic match, I ask myself a question. I have to define the problem. So the problem here is approaching the net better than staying back? That's the question. the sample. This is the statistical sample I'm going to use in the data. It's every rally shot, not every point, right? Every shot within every point. So it's a bigger sample. Every rally shot, in other words, no serves, no returns, because throwing serves and returns in there would just make it even more confusing. I don't want to make it too confusing here. With both players back, I don't want a situation where one player is already at the net, because if one player is already at the net, then he can't be approaching that because he's already there. So the question is approaching better than staying back. The sample, every rally shot with both players currently back at the baseline, having the opportunity to approach if they so choose. The independent variable is like the main variable, the one that we really care about. In this case, that's approaching the net. The dependent variable, these are just more statistical terms. A dependent variable is what depends on the independent variable. So the dependent variable here is winning the point. The point is that winning the point depends on whether you approach the net. That's why we're looking at win probabilities here. And lastly, the confounders. I'm going to throw the confounders into this analysis too, because I have to account for them. Depth, direction, speed of the incoming ball, the same three confounders that I just discussed a couple of minutes ago. Now, my intuition, the way that I expect this to play out here, so I want to kind of go into this analysis with a well-defined hypothesis. Fact one, pros, just like Murray and Raonic, tend to approach on confounders. Right? When you get a short ball, when you get a centered ball, when you get a floated ball, these are all incoming balls coming at you. You get anything like that, you are more likely to approach the net than if you got a different type of incoming ball. In addition, you are more likely to win the point when you get a ball that is short, centered, or floated, regardless of whether you approach or not. Or if you get an easy ball like that, regardless of what decision you make in terms of approaching the net, you have an increased likelihood of winning the point. And as a result, if you put those two facts together, what I expect to see is that confounders are deceptively inflating players' win probabilities at net. Because the point is that you tend to approach the net when you get an easy ball, and it's the easy ball that may be helping you win the point rather than the act of approaching. And yet if you don't account for the confounders, you can't see the difference between those two phenomenons in the data. So now, I'm going to look at the data. So I'm going to throw some numbers at you in the next slide here. These are summary statistics for when I charted this match. So if you look at the left column, this is all for Andy Murray. If you look at the right column, this is all for Milos Raonic. What we see here is that Murray hit 185 rally shots. Raonic hit 206 rally shots. Now, Raunic's number is higher because Raonic is the more aggressive player, which means that points generally tend to end, for better or worse, on Raonic shots. He oftentimes gets the last shot in the rally. Whether it's Raonic hitting a winner or Raonic making an error, Raonic does typically get the last shot, which is why his number here is higher. What you see, for instance, is that on 104 out of Murray's 185 rally shots, 56% of the time, he went on to win the point. Doesn't mean that Murray won 104 points. It means that out of Murray's 185 rally shots that we're looking at here, he went on to win the point 104 times. Raonic, on the other hand, was 98 for 206. His percentage is a little bit smaller because he lost this match. You look at approaches. So out of Murray's 185 rally shots, on 17 of them, 9% of the time, Murray approached the net. Raunic's approach rate was actually much higher, the reason being that he really can't compete with Andy Murray from the baseline, so he came in 25% of his opportunities. And then these are the confounders. So when is the dependent variable approach is the main independent variable, and then you got these three confounders, short, centered, floated. These three confounders are the quality of the incoming ball. So for instance here, when I say 85 out of 185 for Murray were centered, this is not Murray hitting 85 centered balls to Raonic. This is, of the 185 shots that Murray had coming at him, where he eventually hit a rally shot, 85 were centered. So 85 of the incoming balls that Murray faced were centered. Raonic, 76 of the 206 incoming balls that Raonic faced were centered. Then, same thing for short and floated. So I'm going to take this data now, and I'm going to do the statistical analysis on it. And the type of statistical analysis that I'm going to do to answer the main question of whether approaching the net is better than staying back, right? That is the main question. So that's what we keep coming back to. I'm going to use a statistical technique called regression. So the purpose of regression, it's a statistical technique. It is used to model how independent variables affect dependent variables. So in this case, if you want to figure out how does approaching the net affect your odds of winning the point, a regression is a great statistical technique for this because it's designed so that it can account for confounders, right? Just comparing raw win probabilities can't account for confounders. Regression analysis can. So we are applying regressions to our main question of trying to figure out what is the impact that approaching the net has on you winning the point. And I'm going to run 2 regressions. I'm going to run 2 of them for each player. So technically it's 4 total, but it's 2 regressions for each player. The first regression is going to have no confounders. Just going to ignore the confounders, pretend they don't exist. So it's just going to be approaching that and winning the point. And actually, this is the exact same thing as calculating raw win probabilities. I mean, the method's a little bit different, but you end up getting the exact same numbers as if you just calculated the raw win probabilities the way Craig O'Shaughnessy did earlier in the webinar. The second regression for each player is going to be the one with the confounders. So we're going to throw short centered and floated in there. And what's going to happen is we're going to try to figure out, is approaching the net's impact going to be smaller in regression 2? Because regression 2 is accounting for the phenomenon that these confounders can be deceptively inflating raw win probabilities. Now, this doesn't mean that it's going to be a situation where all of a sudden in regression 2, approaching the net is going to look like a bad tactic, right? That's not necessarily the case at all. It might still be a very good tactic. I'm just expecting the impact to be smaller. Maybe that in regression 1, the impact looks really great and big, and that approaching the net is this awesome tactic, and maybe it's still a good one, but not quite as good. This is a regression table. This is pretty much the most, the most involved slide in this entire presentation. It's got a lot of numbers, so I'm just going to kind of take you through it. So if you look at the left-hand column here, what you're going to see are the variables. So we see approach, we see the short-centered floated variables, and we see this thing called constant. So constant, this is not a tennis term. Constant is a statistical term, okay? So if we look at the Murray regressions, so again, there's 185, if you remember a couple slides back. Murray, 185 rally shots. So what we see is we're just going to look at regression 1 for Murray, the one with no confounders. So it's just constant and approach. So the definition of constant, I'm going to say this a couple times, the definition of constant is it is a player's win probability when none of the other variables in the regression are true. So I'm going to say that again. Constant is the player's win probability when none of the other variables that are in the regression are true. So in the regression with no confounders, the only variable that's in this regression is approach. A short-centered floated, not even here. So constant, this 53% number, is just Murray's win probability when approach is not true. So it's just Murray's win probability when he stays back. That's all it is. Murray's win probability when he stayed back was 53%. Now the second number here for approach, this 35.3% number. What's going on with that? Well, this 35.3% number, this is not Murray's win probability when he approached the net. This is the benefit that Murray got from approaching the net. He got a 35.3% benefit. Though this may not be an accurate benefit, this is just the kind of raw win probability benefit. So all it means is that if you want to figure out what Murray's win probability was when he approached the net, just add these two numbers. Just add 53% and 35.3%. So Murray's win probability at net was 88.3%. So his win probability staying back was 53%. His win probability approaching the net was 88.3%. You might be wondering, why am I doing it this way? Why didn't I just report 53% here and 88.3% there? I mean, those are the raw win probabilities. Why didn't I just report it like that? That would probably be simpler. The reason why is because in this second regression here, the one where the confounders get thrown into the mix, all of a sudden actually is a lot easier to present it this way. Because if you look here, right, this 45% number. Now, if you remember, the definition of constant is just the player's win probability when none of the other variables in the regression are true. So this 45% number is Murray's win probability when he doesn't approach, so when approach is not true, and when the incoming ball is not short, and when the incoming ball is not centered, and when the incoming ball is not floated. So this 45% number is Murray's win probability when he stays back and the incoming ball is neither short nor centered nor floated. And that's why this 45% number is smaller than this 53% number, because this is just, the 53% is just Murray's win probability when he stays back. Now this is the 45% number is Murray's win probability when he stays back, and he's not getting an easy ball. Because the thing is, right, short, that's positive. This percentage is positive. Murray has a benefit to receiving a short ball. There is a benefit when Murray gets a short ball. There's a benefit when Murray gets a centered ball. There's a benefit when Murray gets a floated ball. All these three things increase Murray's odds of winning the point. All these numbers, aside from constant, are the benefit numbers. And the key thing to notice here, and this is like if you're going to take anything out of looking at this table, the key thing to notice here are the numbers in bold. We can compare the numbers in bold. So 35.3% is the increase in Murray's raw win probability when he comes to net. This 22.2% is the more accurate benefit to Murray approaching. In other words, the 22.2% is the number when you're accounting for the confounder. So the 35.3% number is deceptively high. The 22.2% number is the more accurate one. And if you look at the same exact thing for Milos Raonic here, it appears that his benefit to approaching the net is 22.8%. In reality, the benefit is more like 16.4% when we look at these confounders. And of course, I could totally add more confounders to this, right? These are just kind of three of the more basic confounders, but there could be others. I mean, the height of the incoming ball, the spin that's on the incoming ball. I mean, there are tons more, even whether it was hit to his forehand or his backhand. There are tons more confounders, and the more confounders you add, the more that the true benefit of the calculated true benefit of approaching the net actually goes down. So what we see here overall is that it is in fact the case that the player's win probability when they approach the net is deceptively high. So just to kind of reiterate the numbers, Murray had a 53% win probability staying back, 88.3% win probability approaching. So his win probability when approaching was 35.3% higher. So you can see his win probability when approaching was 35.3% higher. And yet, a more accurate estimate of how effective approaching actually was for him was just 22.2% more effective. For Raonic, same story, 41.9% win probability staying back, 64.7% win probability approaching. So the win probability when approaching was 22.8%. That is that number here. And yet the more accurate number, the more accurate actual benefit that Raonic had for approaching was just 16.4%. So what you can see again is that because of the confounders, that if you don't account for the confounders, that win probability that you try to estimate for approaching the net becomes deceptively high. So some takeaways from this section of the webinar. Some takeaways involving approaching the net. So first of all, again, confounders deceptively inflate the win probability that players have when they approach the net. You can see that in the numbers. That is in fact what's going on. And as a result, right, if you generalize this, in theory, right, it was not the case in this match, but in theory, you could have a match where a player has a higher win probability at net and yet should approach less often. It was, I mean, if you remember that hypothetical scenario with Djokovic, with the 4 returns, 2 of them were floated. I came into net on both, won both points. 2 of them were hammered. I stayed back. I won 1 of the 2 points. So that was a situation where I had a higher win probability when approaching, and yet if I'd approached more often, I actually would have been worse off. So in theory, you actually can have a match. And later in the webinar, actually, it's not going to be for approaching the net, but there is, in fact, actually a match where something like this really happens. We have a higher win probability doing something, and yet you actually should do it less often. So now, I'm going to get into some further applications of causal inference. So approaching the net, that was one application of causal inference. Again, causal inference is just that statistical term that means figuring out why statistics are the way they are. Causal, cause and effect. Inference, figuring something out, figuring out why the statistics are the way they are. The next application I'm going to give, hitting down the middle. You can see the picture here. Murray's been kind of pulled off the court. He's preparing to hit it down the middle. Raonic is already kind of anticipating that. Now, down the middle is actually kind of the opposite of approaching that. Approaching the net is an offensive tactic. Hitting down the middle is a defensive tactic. You generally hit down the middle when you're on the defensive. So what we actually may see is kind of the opposite phenomenon taking place, right? Where hitting down the middle might have a deceptively low win probability. So I'm gonna run through the same analysis. This is the exact same format. This is, once again, it's a regression analysis. The only difference here is that instead of looking at approaching the net, we're just looking at hitting down the middle. DTM is down the middle. So the question is hitting down the middle worse than hitting to the corners? Once again, the exact same statistical sample. So it's every rally shot that Murray and Raonic hit, no serves, no returns, and both players are back at the baseline. I'm not even going to present a table of summary statistics because the tables would virtually be the same. Again, it's 185 rally shots for Murray, 206 rally shots for Raonic. The independent variable in this case, the main one that we care about, instead of approaching the net, now it's hitting down the middle. The dependent variable, which is what depends, that's why it's called dependent, it's what depends on the independent variable, is winning the point. So we're trying to figure out, well, what is the impact of hitting down the middle on winning the point? And the confounders are the same. Same exact confounders. You have the depth, the direction, and the speed of the incoming ball. It's just short-centered floated. Again, there could be more confounders if you really want to break it down even further. Just for the purpose of this, we're just going to stick with these confounders. So my intuition here, again, just like I did with approaching the net, I need to formulate a clear hypothesis before I look at the data. Fact 1, pros generally don't hit down the middle on confounders. I mean, if you get a short ball, or you get a centered ball, or you get a floated ball coming at you, you're probably not going to hit down the middle. I mean, those are balls I want to attack on. I'm probably going to want to put those in the corners. In addition, you tend to win on the confounders. I tend to win when I get a short-centered floated incoming ball, regardless of whether I hit down the middle or not. Regardless of what I do, I get an easy ball, I'm probably going to win the point. So as a result, right, with approaching the net, confounders were deceptively inflating the player's win probabilities. What I expect here is that the confounders are going to deceptively deflate the player's win probabilities. It should look the opposite. So, I'm going to look at the data once again. Regression table. This is just pretty much the exact same regression table as the previous one. The only difference is the numbers are different now because I changed this variable. So this is no longer approach. This is now hitting down the middle. Short-centered floated, these are the confounders. Down the middle is the main independent variable. We have this constant guy in here. Once again, constant is the player's win probability when none of the other variables in the regression are true. So this 59.9% number, this is Murray's win probability. And the only other variable in this regression, because there's no confounders in this one, the only other variable in this regression is middle. So 59.9% is just Murray's win probability when he doesn't hit down the middle. When he does hit down the middle, his win probability is 14% lower. That's a pretty significant drop. And yet, when you throw the confounders into the mix, you see short, centered, and floated once again. You got positive numbers here because if you receive a short ball, you receive a centered ball, you receive a floated ball, you're more likely to win the point. And based on the the phenomenon that I was guessing was going to happen here, you can see that this negative 9.6% number is not as pronounced as this negative 14% number. So Murray's win probability when hitting down the middle is 14% lower, the raw win probability, yet the more accurately determined impact, it's only 9.6% worse. Same thing for Roundage here. What appears to be something that's 10.7% worse is really only 8.7% worse. So what we take away from this, right, just like how approaching the net was deceptively inflating the player's win probabilities, hitting down the middle is deceptively deflating the player's win probabilities. The confounders are deceptively deflating the player's win probabilities when they hit down the middle. So, right, could we have a match? And again, it's not this one, but could we have a match where you have a lower win probability when you hit down the middle, and yet you should actually hit down the middle more often? I mean, again, it can happen because just because you have a lower win probability when you hit down the middle doesn't necessarily mean that hitting down the middle is a bad tactic, that you should do it less often. And now, this is one specific match. This is like the really cool match where you actually see that crazy phenomenon taking place of something that has a higher win probability, or in this case, it's a lower win probability, and you should do it more often. This is the 2014 U.S. Open Women's Final. This was Serena Williams beating Caroline Wozniacki. Also like this match because of the contrast in styles. You have the aggressive player in Serena Williams, the defensive player in Caroline Wozniacki. The tactic that I'm looking at here is playing behind the baseline, something that Wozniacki did a lot. So I'm only analyzing Wozniacki here, no Serena Williams analysis. And what you see here is Wozniacki, right? Her win probability when she stands behind the baseline is 6.4% lower than her win probability when she's on top of the baseline. All right, so if you look here behind, right, this just means behind the baseline. We have our good friend, the constant term. I can only put two confounders in this one. I couldn't put a floated confounder in here because apparently when I charted this match, Serena Williams didn't really hit any floaters at Caroline Wozniacki because Serena is just incredible and she just wasn't hitting any floaters. But what you see is that you have a situation where Wozniacki had a 6.4% lower win probability when she positioned herself well behind the baseline, like you see in this picture. And yet, when you throw the confounders into the analysis, right, this is just a situation where she's more likely to win the point when she gets a short or centered incoming ball. But when she gets a short or centered incoming ball, she's definitely less likely to be behind the baseline. You have a situation where these flip, right? It looks like playing behind the baseline is a bad thing, and yet when you throw the confounders in, it flips to being positive. Now, that doesn't mean she should be playing behind the baseline all the time. I mean, there are definitely certain balls, and if I broke it down further, there are definitely certain balls, like on a short ball, you definitely want to be inside the baseline. But this is essentially a situation where she had a lower win probability when playing behind the baseline, yet in general, she actually should have done it slightly more often. She was actually a little bit too quick to try to get on top of the baseline. So this is kind of the super most pronounced scenario where she has a lower win probability playing behind the baseline, and yet you should have done it more often. So now I'm just going to run through. I'm not going to do any more statistical analyses here. I'm just going to run through some additional tactics. Swinging volleys, highly aggressive tactic. Players can have really high win probabilities on swinging volleys as compared to regular volleys. Doesn't necessarily mean they should swing in volleys more often. Defensive lobs are the opposite. That's a really defensive tactic. So as a result, the win probability, when you hit a defensive lob, your win probability is going to be really, really low. But that doesn't mean you shouldn't necessarily be hitting defensive lobs. I mean, you do it when you basically already lost the point. So what you're seeing here is that essentially the more offensive a shot is, the more deceptively high its win probability is going to be. Whereas with defensive shots, and if you don't account for confounders, their win probabilities tend to be deceptively low. So again, I'm going to say that one more time. The more offensive the tactic, the more likely it is that the win probability that the player has with the tactic tends to be deceptively high, and vice versa. The last thing here, and this is kind of a unique thing, serves don't have incoming balls. That's why I just want to mention them briefly. Serves do not have incoming balls. Returns have incoming balls. Volleys, ground strokes, they all have incoming balls. Serves don't, right? You just toss it and hit it. I definitely like this picture of Murray serving, so I chose this one on purpose. But the thing here, right, with serves, because there are no incoming balls, this is the one shot where raw win probabilities really do tell the story. So if you look here, right, this is actually from the Murray-Raonic match. When Murray hit his first serve to the ad court down the tee, he won 96% of the time, and yet when he hit his first serve out wide to the ad court, his win probability was only 40%. I mean, he didn't do it very often, but, and again, the sample size is kind of small here, but it does seem like hitting down the tee was more effective than hitting out wide, and there's no incoming balls to confound you here. However, you do have to compare apples to apples. One thing you don't want to do is start trying to pool together first serves and second serves in the data, because then you could have a situation where a player tends to hit his second serve out wide a lot, and as a result, what happens is because players have lower win probabilities on second serves, it suddenly looks like the direction that you tend to hit the second serve tends to be a less effective direction, even though in reality it's not. So that's kind of pretty much the framework here with serves again, no confounders, a little bit easier to analyze them. So the overall takeaways, if you're going to take anything out of this presentation, these are the overall takeaways, not just for this section, but for the entire webinar here. First of all, regression analysis is a highly useful thing to do, right? I mean, this statistical analysis is really useful. It's a great way to quantify the effects that confounders can have on your data. It's a great way, to see whether one tactic is more effective than another tactic. It's a more accurate method than just comparing raw win probabilities. I think that it should become mainstream in the tennis analytics community, and yet it's not the most important thing. Or regression analysis or any fancy statistical technique is not the most important thing. The most important thing is keeping an inquisitive mind. But that's more important than any fancy statistical technique that you can come up with. If you keep an inquisitive mind, if you ask yourself when you're looking at the data, why are the data the way they are? Why are the statistics the way they are? Even if you can't fully quantify it because you don't have that statistical toolkit, even if you just ask yourself, why is my player's win probability net high? Why is my player's win probability when he hits down the middle low? That goes a long, long way. You don't necessarily need the statistical background. In fact, I can prove it. This is it's a non-tennis story. Just like the Dr. Wald story was a non-tennis story. This is a story of a guy who had no statistical background whatsoever. I was not a statistician. Dr. Wald was a great statistician. This guy was not a statistician, and yet he, in my view, conducted the most important, the most consequential statistical analysis of all time. And he got it right. It's a story of Lieutenant Colonel Stanislav Petrov. He was a lieutenant colonel in the Soviet Union in 1983. The Soviet Union had just installed a new computerized missile defense system that was essentially doing statistical analysis. patterns of light that were in the sky, and Petrov was the officer tasked with reading the machine. And all of a sudden, one morning in 1983, the machine, the statistics were basically saying that the United States had launched 5 nuclear missiles at the Soviet Union, and they were incoming. And Petrov had to decide, do I retaliate? I mean, do I shoot nuclear missiles at the United States? The machine was telling him to do it. And yet Petrov, instead of just going, oh, well, that's what the statistics show, let's retaliate, he stood back. He's like, wait, what's going on here? Why are these patterns of light the way they are? I mean, first of all, is the United States crazy? And second of all, if they were really going to be shooting nuclear missiles at us, why would they only shoot 5? Right? That doesn't make any sense. And if they're only shooting 5 missiles at us, we could totally retaliate on them. Surely they would shoot a lot more. So what Lieutenant Colonel Petrov realized is this is probably a false alarm. That something's going on. There's some sort of confounder. In this case, what it was that there was a weird cloud formation, and the way that light was reflecting off the cloud was triggering the machine to have a false alarm. And as a result, because Petrov, he thought, why are the data the way they are? He interpreted the statistics correctly, and the guy literally saved the world. I mean, he's the reason why we're all here today. Now, fortunately, as tennis coaches, we do not have the fate of the entire planet on our shoulders. And this is the second promise, right? This is the second promise. The first promise, which I gave, earlier in the talk, about how you're never going to look at statistics the same way again. This is my second promise, which is that whether you have statistical training or not, if you keep an inquisitive mind, if you ask yourself, why are the statistics the way they are, then as tennis coaches, you are going to be able to provide the best possible service for your players. And really, I mean, providing the best possible service for your players is what being a tennis coach is all about. So that is now, in fact, the end of this webinar. This is my contact information. I'm going to leave the slide up for a couple minutes if anybody wants to take it down. It has my address, my phone number, my email, my website. So I'm just going to leave this up for a bit. And that is the end of the webinar. And I can now, we have about 10 to 15 minutes left for Q&A. So as far as questions go, it's probably easier if Jason just reads them to me. I'm trying to see if I can find them here in the chat. So again, if anybody has any questions, you can just type them in. So I see from Jason Joseph, yeah, very true. Agassi had a win probability at net of nearly 80%, yet he did not morph into a net rusher. That is absolutely the case. I mean, especially Agassi was super, super selective with when he came into net. So as a result, I mean, Agassi really only came into net. And maybe Agassi should have come into net more often. I don't know. I've never analyzed his matches. But when you have a situation like Agassi, he's generally coming into net on balls where he probably would have won the point anyway. So that's really going to inflate his win probability at net. But yeah, so again, if anybody has questions, you can type them in. I'll just wait here, for a couple more minutes to see if anybody is typing in any questions. And yeah, so.
Jeremy, out. You know what I'll do is while we give everybody a moment to kind of decide if they want to ask a question or not, I'll ask you a question. So I know, oftentimes you were talking about first serve placement and second serve placement and how they'll differ, and certainly that's the case. Is there a way statistically that you can look at what some of the more important points in a match, right? So one thing that I've learned over the years is one of the most important serves to train is a second serve to the ad side, right? Because most big points, right, is a higher percentage of chance that a game point will happen on the ad side. And so
Correct.
as a coach, training, especially training the second serve where players are under pressure and will either have to get themselves out of a situation of being down a break point, right, or trying to convert while hitting a second serve. That's one of the more important things to train. Anything that you know of statistically where you find that it would be important for coaches to train their players?
Are you specifically referring to serves, or are you just referring to things in general?
I'm referring to things in general. I gave the serve example, and I think you know, your point that when serving, you're not receiving a ball. It's the only shot in tennis that you're not receiving a ball, right? You're
Yes.
placing your toss and you're executing. So that is one of the easier things to be able to research, get data analysis on, and certainly as coaches to train. So whether it's serve or anything else that you know of that could be pretty valuable for coaches, right? To be able to know that it's going to be an important thing to train.
So this is actually something that Craig O'Shaughnessy actually does. This is my favorite statistical analysis by him. So I was being a little bit critical of his statistical analysis in terms of like win probabilities when approaching the net. But one thing I think which is great, which Craig O'Shaughnessy does, is he emphasizes the first four shots um, of every point. You know, the serve, the return, the first ball that you hit after the serve, and the first ball that you hit after the return. Because I mean, the thing is, you know, and again, this is just him saying this, but you know, players tend to practice rallying a lot. And that's not to say that you shouldn't practice rallying. And the reason for that is because, and I mean, other coaches have said this, you know, practicing rallying helps get players in the mindset of grinding, of being consistent. Sometimes just even that mental thing is something that can make your opponent play worse. And really, you know, like psychology in tennis matters by a lot. Having said that, though, it is really definitely important again to practice those first four shots, the serve, especially even the first two shots, the serves and the returns, because you generally see that all the time. So I mean, again, like from a statistical perspective, if you're gonna practice something, like make sure that you're putting adequate emphasis on practicing things like serves and returns and what comes immediately after that. Um, but yes, that's the thing that's coming to my mind right now. I mean, of course, you know, I'm sure at some point after this presentation, you know, 3 hours later, something else is going to pop into my head. And I'm like, oh man, why didn't I say that here? But that is
Yeah,
that's
that always does. That's all right.
yeah, I mean, it happens all the time. There's, you know, I've just learned to live with that. So
Yeah, absolutely, for sure. All right. Well, I think that wraps it up. So everyone, you know, the information is up on the screen. Feel free to email Jeremy or shoot him a call with his phone number, and certainly check out his website, topspinshotresearch.com. Jeremy, thank you very much for taking the time today to present and give us some statistical analysis on tennis, especially the aspects of approaching the net.
all right, you're welcome. And thank you for helping to set this thing up. And you know, everybody, stay healthy and take care.
You as well, Jeremy. Thanks everyone for joining today in another USPTA Eastern webinar series. Thanks, Jeremy. Take care. Thanks, everybody. Bye.